Alrighty guys, this is like my third time filming this video, so hopefully this one doesn't go as bad as the other two. So we'll see. For number 4, we want to find the area of the region bounded by the graphs of x over the square root of x squared plus 1 and x to the 4th minus x. Okay, I already have that in my y1 and y2. We're just going to graph it. So do that in y1, y2, graph it. Looks like that. It's not the best thing. So what we're going to do here is probably change our bounds from 0 to 2 and then negative 1 to 1. 0 to 2, negative 1 to 1. Graph it. That looks a little bit better. And then what we're going to do here is look at your top minus bottom. So your top function is going to be the blue function. Your bottom function is going to be the red function. My blue function here is x over the square root of x squared plus 1 minus x to the 4th minus x dx. Now we know that my intersection is at 0 here. That's my lower bound. And then my upper bound, whenever I try and make infinite limiting rectangles, I stop at my intersection, but we don't know what the intersection is. So we're going to do second calc intersect, see what we get. AKA 1.180. Now that would be your setup in terms of an FRQ. Now here's the thing about this right now. If you don't do anything crazy, the 84 will actually store x as 1.180 unless there is a new x involved. So in this case, what you can do here is do the integral from 0 to x of y1 minus y2 dx, and that's going to give you 0.7853. Now, if you don't believe me, what you could do here is go ahead and do the same thing, but with 1.180, and you could see that we get 0.78538. Then, of course, our approximation of 1.180 isn't the best. So, but at least it's good with up to, what is it, like the 4th or 5th decimal point, which is fine. Good enough for me. All right, so for number 7, I'm going to graph sine of x, cosine of x, and then I'm going to change my bounds from 0 to pi over 2. We might have to change our y-min or y-max, but we'll do that later. Okay, what's going on? See, I'm not a big fan of these online calculators. Sine of x, cosine of x, graph them. Oh, okay, that's actually perfect. Maybe. Well, I'm gonna change my y-max to be 1.25 just so that I can see the tip. Okay, now whenever it says the region sine of x, cosine of x, x is equal to 0 and x is equal to pi over 2, I am talking about this region right here and this region right here. So to find the area of the region using two different integrals, for the first one, notice how I'm going to go from my intersection. I'm going to figure out what that is. And then notice how my top minus bottom for my first part is cosine, which is red, minus sine, which is blue. And then after that intersection, notice how my top now changes to my blue function. So then my top is sine, and then my bottom is cosine. Now, essentially, hopefully you know this by now, but sine and cosine are the same when x is equal to pi over 4. So that means that my intersection is at pi over 4. So to set up the integral using two different integrals, I'm going to go from 0 to pi over 4. And then I'm going to do my top minus bottom there. My top is going to be cosine. My bottom's going to be sine. And then I'm going to add pi over 4 to pi over 2. My top is now sine. And then my bottom is cosine. So that's just me splitting it up. Because we have a different top minus bottom before pi over 4 and a different top minus bottom after pi over 4. Now this is going to take a while for me to type this in, but bear with me. Let's see, cosine is y2, so I'm going to do y2 minus y1 here. y2 minus y1 plus the integral from pi over 4 to pi over 2. We're going to do y2 minus y1. Oh, Jesus. Oh, wait, it should be y1 minus y2. Sorry, guys. Oopsies. y1 minus y2. Then that gives us an area of 0.8284. Now, you kind of saw earlier here that this area is 0. So basically that just means that the area from 0 to pi over 4 and then the area from pi over 4 to pi over 2 is essentially the same thing. But remember how I told you that area can't really be negative and it really can't be 0. So your answer here is just going to be 0.8284. Now, setting up that integral was a lot in terms of splitting up the bounds at pi over 4. Now, there is a way for you to not split up the bounds. In this case, what we're going to do here is actually go straight from 0 to pi over 2. But we're going to take the absolute value of cosine of x and sine of x. So if I do the integral from 0 to pi over 2, we're going to do the absolute value of cosine. What's cosine? y2. So y2 minus y1. And notice how you'll get 0.8284. Oh, but here's the thing. More magic. If I do y1 minus y2, if I do y1 minus y2, that also gives us 0.828. So if you are given a calculator active question and you don't know what your top minus bottom is, just use absolute value bars and you'll automatically, most likely, get your answers 99% of the time. So, you could always use what you did in part B, aka put absolute values for any general region, if you're given a calculator, obviously. If not, then you're going to have to split up the integral just like what we did in part A. And essentially what this just does is, remember how this area right here was 0 because it kind of got canceled out with the first integral. But if I put an absolute value bar, that negative area becomes positive area, and then you'll get 0.8284. All right. For this one, you just have to visualize this, okay? One of them is negative and then one of them is positive. Top minus bottom. So in this case, your top is going to be f of x. Your bottom is going to be g of x. So then once you do that, you're going to get negative 2x squared minus x plus 6. Which means it can't be C and it can't be D. It's either going to be A or B. Now remember, in order to find the bounds, you're just going to set f of x and g of x equal to each other. Which, if we do that, we'll get 2x squared plus x minus 6 equals 0. Now, if you factor that, you're going to get x plus 2, and then 2x plus 3. Or, no, 2x minus 3. And then once you solve for 0 to get your bounds are going to be negative 2 and 3 over 2. Which gives us answer choice B. All right, number 9 is a calculator active problem, so we're going to use the calculator here to sketch this out, maybe. We'll see what happens. One over x squared, y is equal to 4, and then y is equal to x. Okay, this is... Let me change my bounds. Oh, Jesus. So 0 is definitely 0. And then that's definitely 0. Okay. Now, the problem with number 9 here is that I really can't do top minus bottom. Well, hypothetically, I can, but... Well, actually, you know what? I'll just do it both ways for you guys. Hypothetically, I can do top minus bottom here, but I just got to separate it in terms of my intersection between the blue line and the black line in terms of top minus bottom. So this would be 4 minus the blue line first. And that blue line is 1 over x squared. And that is going to be from my first intersection. Oh, beautiful. My first intersection, which is at 0.5. And then my second intersection, which is at the bottom, aka my blue and my black intersection. That's 1. So that goes from 0.5 to 1. So basically, if I were to draw this out, it's this part right here. Now this part in purple, I'm going to start at 1. I'm going to do top minus bottom, but now it's going to be 4 minus x. And then I got to find the intersection at the very end, so my third intersection. So, with this example right here, you'll notice that I'm kind of doing a lot, but you'll still get the same answer. That's 4. That is not pretty, but we'll do it. So you'll get the integral from 0.5 to 1 of 4 minus 1 over x squared. I know it's like already saved, but I don't know what's what. Plus the integral from 1 to 4 of 4 minus x dx. And that gives us an area of 5.5. Now notice how, once again, That was a lot because we had to split it up into two parts in terms of my top minus bottom. Now, did I really want to do that for number 9? Probably not. Make your life easier, okay? Notice how you could do right minus left, aka the black line minus the blue line. So I'm just gonna move this. Now, you'll still get an answer at 5.5, but you'll see that the second method is gonna be a little bit easier, but we gotta solve this in terms of y now. Now, lucky for us, this is already in terms of y, so y is equal to x. This one here, we need to change it a little bit. This is going to be x squared is equal to 1 over y, and then x is equal to plus or minus 1 over root y. We're taking the positive counterparts because it's in the first quadrant, so then we get 1 over root y. Now, our bounds here, we know that our upper bound is going to be 4 because it's y is equal to 4. Now, my lower bound here, let's see. Can I trace this? No, oops. Trace 1. Okay, so my lower bound here, according to my intersection, is 1. So I'm going from 1 to 4, and if I'm doing right minus left, it's going to be the black line, which is y, and then the left line, which is 1 over root y. I'm going to go ahead and take the integral of this from 1 to 4, even though this is going to be x. Remember that that's just a placeholder for me saying y in terms of my actual integral that I have on the page. But you can see how here that only took me a couple of seconds. Granted, I did know what the intersections were because of the first part, but still, notice how doing right minus left is a lot easier than trying to split up the integral. Like this one here, if I were to ask you to find this area right here, I would prefer you guys to do right minus left here instead of splitting up the integral, okay? Now, unless they specifically tell you to put it in terms of dx or specifically tell you to do it in terms of dy, do whatever is most efficient. I'm going to skip 11 and 12 for 2 seconds, and then we're going to come back to that. I want to do the FRQ here. And what we're going to do here is actually go ahead and put this into the calculator. Okay, what's going on? Why does it keep on doing this? ln of x plus 3, and then x to the 4th plus 2x to the 3rd. They intersect at -2 and b. So notice how here, if I'm going to copy this graph right here, it's from -2 to 1, and then maybe -1.5. Actually, no, let me do -2. -2 to 2, just to be safe. Ooh, that's nasty. It works. Find the area of the region enclosed by the graphs of f and g. Okay, so we need to figure out what f is, and we need to figure out what g is. In this case, f is going to be this function right here. Oh, let me do that in blue because that's in blue. And then g is going to be my red function. Now, because they give you function values, function names, and this is a calculator answer problem, use a function name. So you're going to say f of x minus g of x. The reason why we didn't do function names here is because this is y, and this is y, and this is y. Same thing here, this was y, and this is y. Same thing here, this was y, and this is y. So if they give you function names, then use the functions. We know that we're starting at -2. We just need to figure out what b is. So we are going to do second calc, intersect, find out where the intersection is. Oop, what's going on? Okay, I think you kind of glitched, but your intersection is at 0.781. So B here is 0.7819. Now, here's the thing. Because it tells you x is equal to b, you can name this as b. That's fine. They'll give you at least 1 point here for giving me the correct setup. And because you named b here as 0.7819, you do not have to repetitively write out 0.7819. You could just write b. Now, that integral is from -2 to x, or in this case b, of top minus bottom. And that is 3.6035. Now, for number 2, it says for -2 to b, let h of x be the vertical distance between the graphs of f and g, aka this black line here, the vertical distance, 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 the vertical distance. Now, it's asking us, is the vertical distance increasing or decreasing when x is -0.5? Well, if h is the vertical distance, aka top minus bottom, then my height of each rectangle or each distance is going to be f of x minus g of x. And since we want to see if h is increasing or decreasing at h is equal to -0.5, I'm going to take a derivative. And then I'm going to plug in -0.5 and see what happens there. So that means I'm going to do math 8 x y1 minus y2 at -0.5. That gives us -0.5999. Therefore, the vertical distance is decreasing at x is equal to -0.5 because h prime of x is negative there. All right, and that was 13 in terms of the area problems. All right, go ahead and put 11 into the calculator, if I can, on my Buddha. I don't know why it's, okay. Maybe it's just because I have fat hands or something. I have x cubed, 4x, and it's in quadrant 1, so I know that my bounds have to be from 0 to something. I'm going to say 3 for now, and then 0 to 3, and then I'll change it later if I need to. Oop, Let me change that to like 8. Okay, it was exactly 8. Okay, so this is what our graph looks like. This is 0, 0, and this is 2, 8. Now it says consider the region in quadrant 1 bounded by the functions y is equal to x cubed and y is equal to 4x. Find a value of k so that the line x is equal to k divides the region into 2 regions of equal area. So you have a line x is equal to k, meaning that we have some k value. So some line that's going to split up this region so that region 1 is equal to region 2. Okay. Now, we don't know where this line is going to split it up, but we know that it's going to be a line. Now, to set this up, there's a couple of ways for you to do it. The first way is to actually find out what the area is and then divide by 2. So, for example, if I know that my intersection is from 0 to 2, and then my top is 4x, so that's y2, so y2 minus y1, that's an area of 4. So we know that this right here has an area of 4, which means that this has an area of 2 and this has an area of 2 whenever we split up the lineup. The problem is we don't know what it is. So you have a couple of ways to solve this. You could go from 0 to k, knowing that k has to be between 0 and 2, and you could set this equal to 2. Or you could do k to 2, and then 4x minus x cubed, that's equal to 2. So basically this here is my first region before the split up. And then this here is my second region, aka after the split up. And then you could use FTC to figure out what k is. Another method is also setting the two equations up without even finding out the area was 4. The whole area was 4. Oops, that is bad notation. Oh my god. Bad notation. I would mark points off if you did this. So make sure that you have your dx's. So this is another way for you to solve this. Now, if this was inactive, you would just use FTC, find k, call it a day, right? Now, if this is active, then here's what we're going to do. And it's a secret trick that I've been gatekeeping for like 4 months. Now, the problem is some of your calculators will not have this. It's the numeric solver, and I'm going to teach guys how to play around with the numeric solver. So you're going to go to math, you're going to go all the way to C, which is at the very bottom, and then what we're going to do here is literally do the integral from 0 to x of, let's see, y2 minus y1 dx, and then the integral from x to 2 of y2 minus y1 dx. Now notice how you have OK right here. That OK means that you're going to hit graph. So graph is OK. Don't hit enter, hit graph, because graph is OK. Once you hit graph, you are going to set your bound to be 0. So we're going to let x be 0 for now. Your bound is going to be that. Don't change it. And then you're going to click on solve. And remember, that just means graph. So click on solve or graph. And this is the point where it probably might, oh, no, it didn't take us a while. So your answer is going to be 1.082. So basically this means that this line right here is 1.082. Meaning that from 1.082 to 2, that gives us an area of 2. And then from 0 to 1.082, that gives us an area of 2. Now, I'm also going to show you... Oops. Ooh, Jesus. What's going on? Ooh, okay, let me just... I'm also going to show you that you could say 2 here. I'm going to press that to 0. Always put that as 0. Then you're going to hit solve or graph. It's going to take a while. And then you see that x is 1.08, just like we had earlier. Now, we're going to do the same thing with number 12, except this time it's y is equal to m, which means that everything needs to be in terms of dy. Meaning that I have my little graph, 2 to 8, 0, 0, and then it's a horizontal line. Y is equal to m. Now, because it's a horizontal line, and like I said, everything needs to be in terms of y, this means that my integral is going to be from 0 to 8 dy, and then we have to do right minus left. And here's also one good thing about number 12. You already know what the area is. The area is 4, that never changes. So this is so too, that never changes. The only thing that's changing is that instead of a vertical line, we have a horizontal line. So now we have the integral from 0 to m, the integrand, and then that has to equal to 2. Now we have to do right minus left between my cubic function and my linear function. My cubic function is going to be the cube root of y, and then my linear function is going to be y over 4. So whenever I do right minus left, I'm going to do the cube root of y minus y over 4 dy. I'm going to quickly do this in the calculator. The integral from 0 to x, okay, so you probably want to change this because it is now the cube root of x minus x over 4. And then that's still 2. Graph, 0, solve, and then that gives us y is equal to it's going to take a while. 2.828. You could verify that also works with the other methods that we learned earlier with number 11. But I'm going to tell you that number 11 and 12 are going to be very, 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 very important in terms of those FRQ questions that you'll see on the AP exam.